Okay, welcome back. And today we'll see details of the amplifiers used across the deflection plates, that is horizontal amplifiers and vertical amplifiers. And before going into the details of those amplifiers, I missed 2 points in the last few lectures. One is that, see, we are applying such a sawtooth waveform across the horizontal deflection plates, and this signal is called a sieve generator. We know that. But when we when the voltage is in this part, when the signal is in this part, we know that the stylus or the pointer will move from A to C via B. And when this is the circuit, this is the waveform of the sieve. If this is the part of the sieve generator, then we know that the stylus will retrace from C to A via B. But one thing is very simple. While we switch on the CRO, we will see the trace moving from A to C, but we will not be seeing, we never see the stylus moving back from C to A. The retrace part we are not seeing. So we are not seeing because that is already there, but we are not seeing because that is actually masked from the viewer, or that is blanked from the viewer by a suitable circuit called blanking circuit. So that retrace path is never shown in on the CRO screen, or it is actually masked from the viewer. Okay, and that is masked by a circuit called blanking circuit. That is one thing. And the next thing is that yesterday we have seen a basic circuit of a sieve generator, where we have a capacitor that is being charged through a resistance R towards VCC, and we apply a train of pulses. When we apply, this transistor will turn on and the capacitor will find a suitable path to discharge. So we achieve a shape like this: charging, discharging, charging, discharging. Okay, so it moreover resembles a sawtooth waveform, but we can see that the charging as well as discharging equations are exponential. This is exponentially growing and this is exponentially decaying. So in that such cases, it's non-linear. We expect a linear curve. Okay, so this circuit is never used. That is one thing. This is to give a basic idea. Okay, so this is a basic time-based generator, and I have told that that is during this lecture, that is okay. So there's a little technical confusion here. So see, when I vary the sawtooth waveform frequency, indeed I am varying the time period. That is, this by means what I mean by 1 millisecond. When I mean by 1 millisecond, the thing is that the trace will take 1 millisecond to travel from A to C. And what is the meaning of 0.1 milliseconds? That is, the trace will take only 0.1 milliseconds to travel from A to C. That means you are actually varying the speed of the stylus or the pointer. Okay, so how do you actually practically implement? You have a times per division scale, times per division knob there, and around that knob you can see such values. So how do you vary practically? How do you practically achieve speed variation? Okay, that is what is done here. So the thing is that okay, how do you practically achieve that? See, there is a capacitor here. So this capacitor actually will vary. So there are multiple banks of such capacitor. So when you vary the times per division scale, you can see over the scale that values like 1 millisecond, 0.5 microseconds, 10 milliseconds, such values. So how do you achieve that? You vary the capacitor. There are some bank of capacitance. So by varying that selector switch, you are selecting different values of capacitor. So what is the big gain in varying the capacitor values? You're keeping the value of R constant, but you're varying the capacitor. Different capacitors you are adding, okay, at different times. So while you do that, you're actually varying the time constant, which is RC. So what is time constant? Time constant is directly proportional to time period. So when you vary this capacitor, you're varying the time period, and when you vary the time period, you're varying the vary the time constant, you're varying the time period. So by varying different capacitors, by putting different capacitors, you are actually varying the time period, thus varying the velocity of the stylus. This is one thing I have to mention. And then coming back to a practical circuit which are generally employed in a CRO, see, that is, see here we are actually moving using a common a constant current generator, that is a constant current generator is there which will charge the capacitor. So if it is a constant current generator, the capacitor also will charge at a constant rate, and that was a problem in the previous circuit, that is exponentially charging and exponentially decharging. So that was the problem. That is why we got a non-linear relationship. Here we are avoiding such disadvantage by having a constant current generator, and this constant current generator will charge the capacitor. And one difference is that we are typically keeping a very high value of resistor. Okay, so by keeping a very high value of resistor, what happens is that this is, see, this circuit is actually a common base configuration of a transistor Q1. It's a common base configuration. So we know that the base emitter junction should be always forward biased, and the collector base junction should be reverse biased. That is how these supplies are connected. So by keeping a very high value of R here, so what we are doing is that, see, the emitter current will more or less become a constant current. By having a very high value of R here, the emitter current becomes more or less a constant current. If that is the case, then the collector current also will be a constant current, because emitter and collector is having a constant relationship, linear relationship. We know that alpha is equal to IC by IE. So if IE is constant, then IC also becomes constant. And we know that these are the output characteristics of a common base configuration. Okay, so VCB plotted against IC, keeping IE constant. So in this part we know that IE is a constant, so IC also becomes constant. So keeping this in mind, this characteristics in mind, if we keep IE constant, IC also become a constant. So this IC will charge the capacitor. So when IC charges the capacitor also charges constantly. So we'll get a more or less linear charging and linear discharging. How will you get the linear discharging? So we, just like the previous circuit, we apply a train of pulses so that we'll discharge the capacitor regularly in regular time intervals through this transistor. Okay, so this is what is there. And now we move on to the next thing, that is the vertical amplifiers. See, vertical as well as horizontal amplifiers. Why do you require vertical and horizontal amplifiers? See, ultimately you have to ultimately the CRO has to faithfully reproduce the signals that we are giving to the CRO. Okay, so we require amplifiers both across the vertical deflection plates as well as after the horizontal deflection plates. Okay, now one thing that should be kept in mind, that we have learned in analog electronics course, that, see, the gain bandwidth product of any amplifier is a constant. I repeat, the gain bandwidth product of any amplifier should be a constant. See, typically this is the quality of any amplifier. This should be the quality of the amplifier which should be after the vertical or the horizontal deflection plate. That is, the amplifier should be able to amplify signals right from DC to a signal having some frequency. So this is the highest frequency which the CRO can accept. So each CRO has its own upper limit. It can be 35 megahertz, sometimes it can be 20 megahertz. So it has a certain cap. It can amplify high frequencies, but there is a cap. So this is the cap for this particular CRO F2. That is, it can amplify signals or faithfully reproduce signals up to a frequency F2. So how do you define bandwidth? This is how I define bandwidth. That is 3 dB frequency. That is, we take the 3 dB fault, the gain fall by 3 dB, and this is the point. And from this point to this point, we have the bandwidth. So this gain, the gain should be constant. We always take that. We always have for ideal case of an amplifier, there should be a considerable portion of frequencies where the gain should be constant. So this is the gain region of frequency or range of frequencies for which the gain is constant. So this gain multiplied by the bandwidth is always constant for an amplifier. Okay, so that is one thing that should be kept in mind. And another thing is that the thing is called a vertical sensitivity. What is a vertical sensitivity? So it is vertical sensitivity is a measure of how much an electron beam will be deflected for a specified input signal. That is, how much an electron beam will be deflected for an input signal. See, of course, we have seen another knob called volts per division. We know that one complete block is 1 centimeter, and each minute division is 1 millimeter. Okay, so that is how it is labeled, but we always call it as volt per division. So what is vertical sensitivity? If it is 5 millivolt per division, if I place the knob at 5 millivolt per division, then what is the meaning? That is, when you apply an input signal, that will cause, if I apply an input signal, then that input signal, if it is 5 milli, that if, however small that input signal, that will cause 1 millimeter deflection. That is a small, that is a sensitivity, that is that it will cause a 5 millivolt deflection, or that a 5 millivolt input signal will cause 1 mm deflection in the vertically. And if is apply a signal in volt, then if you have, suppose if you set the knob at 5 volt per division, then it requires an input signal of 5 volt to cause a deflection of 1 millimeter. I think it is clear. That is, if it is 5 millivolt per division, then if you apply an input signal of 5 volt, then it will 5 millivolt, it will cause a deflection of 1 millimeter. Whereas if you apply a signal of 5 volt, then that will cause, if the knob I place it at 5 volt per division, then that will cause a deflection by 1 millimeter. So which is the greater sensitivity? Greater sensitivity is 5 millivolt per division. That is, when you apply a signal of 5 millivolt, it will cause a deflection of 1 millimeter. And what about the next thing, that is 5 volt per division? If we apply an input signal of 5 volt, then it will cause a deflection of 1 millimeter. Of course, 5 millivolt per division is having more vertical sensitivity. So that is the difference of vertical sensitivity. So vertical sensitivity is actually around the knob of volts per division. 5 millivolt per division, or 1 millivolt per division, or 2 volt per division. That such values you can see. So what is the lowest value will actually account for the highest sensitivity. Okay, so this is around the panel. Okay, now this vertical sensitivity is directly proportional to the gain. Okay, so if you want to have more vertical sensitivity, then you can have, then you should of course have larger gain. If you want larger gain, then that should be at the expense of bandwidth, or the bandwidth which should be sacrificed for more gain. Okay, so if you want more bandwidth, then you have to sacrifice gain, then you have to sacrifice vertical sensitivity. So there is a mutual trade-off between vertical sensitivity and bandwidth, or gain and bandwidth. So properly you have to choose these things. And another thing which is a great requirement for a vertical amplifier is that, so one thing we have to see, two things we have seen, that is bandwidth and vertical sensitivity. The third thing the vertical amplifier should have is that the rise time. Probably this is a new term for you. That is, when you apply a suddenly varying pulse or a square wave. Square wave, we know that the initial portion of a square wave will be suddenly vertically increasing. Suddenly, in no time, the signal will be increasing. So the amplifier response also should be suddenly varying. We expect a faithful reproduction. So vertical amplifier also should suddenly increase, and that is, so the increase will always depend on the rise time of the amplifier. So what is rise time? This is the formal definition of rise time. That is the time taken for the vertical amplifier to increase from 10% to 90% of its maximum amplitude. A square wave will have maximum amplitude. So how much time the vertical amplifier require to increase from 10% to 90% is actually the rise time. So faster the rise time, the lesser the rise time, then you can expect faithful reproduction of that square wave or the pulse. So these are the three requirements of vertical amplifier. One is gain, second is bandwidth, and third is the rise time. So vertical sensitivity is directly proportional to gain, so that is there. And bandwidth, what is the largest frequency that a CRO can accept will depend on the bandwidth. And the rise time, that is how fast the amplifier can vary according to the square wave or pulse that you apply. That is actually given by the rise time. So these are the three things that you have to learn in vertical amplifier, and this is the block diagram which we'll see in the next class. That is, this is the vertical amplifier. This vertical amplifier will be having a pre-amplifier as well as a mainframe amplifier. So this amplifier in itself will be a lot of different stages, and this amplifier will be also multiple stages. Okay, we'll see in detail all these things in the next class.